Okay, so now a more detailed animation of what's going on inside a flock. So this big flock that I have on the right is like a big blue flock that I showed previously. Just now I'm showing the detail and showing you actually it's extremely porous. It's this fluffy like snowflake, and it's hanging out in the flock filter, and water is flowing around it, and water is also flowing right through it. So those are streamlines, and some of those streamlines go right through the flock. Not many of them, but a few of them. And so the dark blue in the middle here represents the flow that actually ends up going through the flock. And the donut between the dark blue and the outer blue ring represents kind of the projected area of the flock where that water goes around the flock. So the point is that most of the water still goes around the flock, but a small amount of it goes through, and that small amount ends up probably pretty efficiently being filtered by all of the particles that are inside the flock. So that ratio of the dark blue to the white is a function of the flock porosity or the fractal dimension, but think about it as flock porosity. If the flock is really porous, then lots of water can flow through it. If it's not at all porous, then the dark blue dot goes to nothing, right? If this were a non-porous sphere, then no water would be flowing through it. And that ratio that I've shown here would be 0. And it wouldn't work anymore. So let's animate this and show what's going to happen. So let's get rid of these streamlines, and let's bring a flock that came from the flocculator, and it's going to come up from the bottom of the screen, and it's going to either go around this flock, or maybe if we're lucky, it will go right through it. So let's see. Up, I lost that one. It just went around. Let's try another one. This one was closer to the center, and it actually went into the flock and got caught. Here's another one into the center of the flock and got caught. Another one got caught. And now the flock is apparently has some human characteristics, and it's feeling full. So the flock is like, oh man, I've just eaten a lot of clay. I'm feeling full. Another clay particle comes in, and it manages to, it goes into the flock and gets caught. Another one goes in and gets caught. And the flock is saying, oh my goodness, I'm stuffed. And now the flock's porosity has been reduced. So there's very little water that's actually flowing through the flock anymore. The water is instead flowing around the flock. And so now when we send another particle up through in that same spot, it just goes around the side. So this flock is now one of those blue flocks with lots of red dots in it, and it's full, and it no longer is capable of catching any more red dots. So here we have uniform flow up through, and although there is some shear associated with the fact that it's flowing around flocks, there's no big fluid deformation happening. So I'm not going to say that these flocks don't rotate at all, but there's nothing spinning them like there was before. Isn't that a great insight? So before we said this couldn't happen in the flocculator, but here the fluid dynamics are completely different. And so these flocks are not spinning wildly, they're just hanging out. And now this effect that water can actually flow through the flock because it's no longer dragging all this boundary layer around with it. And we have this new mechanism for capturing little particles. I want to end with this slide, because this slide gives you a little bit of an insight into how we go about trying to figure out what's happening inside a process where you can't actually see it. So this is data, and I should have put a citation here. It's from Kevin Sarmiento's thesis that he just completed for his master's. And he was using particle counters that can count and size particles that were leaving a flock filter. And he's tracking, okay, on the y-axis, it's delta PC star. That means that from at time 0, when his system just began working, he called that 0. And so what he's tracking is additional improvements in performance since that time 0. So a delta PC star of 1 means that he's removing an additional 90% of the particles. And a delta PC star of 2 would mean he's removing an additional 99% of the particles. So here we're seeing time 0, he's basically set it to 0. And then we're looking at the improvement in performance. And over the next few hours, up to about maybe 7 hours, the flock filter is slowly. So I have a confession to make. I'm in the process of changing language about how we talk about this stuff. And I have just concluded that we should talk about these as flock filters rather than flock blankets. And I'm chuckling inside because one of the flock blankets leaked through onto this slide. So I didn't get rid of all the flock filters. So anyway, the flock filter is growing, and eventually it starts dumping into the flock hopper. And the moment where it starts dumping into the flock hopper is at like around hour 7. And you see that there's this very interesting trend. Okay, and there's all these different particle sizes ranging from 2 to 3 micrometers up to 33 to 65 micrometers. And then there's also just the turbidity meter that measures all the particles that are in there. And you see that there's little differences in the trends, but let's focus on the group of particles like between 2 to 3 and all the way up to 5 to 9 micrometers. These are mostly the clay particles that were introduced into the system, because there's a range of sizes within clay. And what we see is that they all got better as the flock filter was growing in depth. And then when the flock filter started dumping excess to the flock hopper, performance actually got worse. And this was a complete surprise to us. We didn't know this was happening. We had made a mistake, and we had done a lot of research where we built different flock blankets and we measured their performance as we were building them. And we hadn't done an extended experiment where we looked at how did that flock filter continue to work after it was running for days, because this is just a little over a full day that this experiment was running. And here we see that it gets worse and worse over time. And this made us think a lot about what could possibly be happening that makes it that when a flock filter reaches the flock hopper and starts dumping flocks, that it gets worse. And I showed you the hint of what it is. And it's that at that point, some of those beautiful blue flocks, before they've ever had any chance to capture any of the red particles that we're trying to remove, get wasted and dumped. Before that time, none of them get wasted because we're not wasting any flocks. So it's once the flock filter gets to the flock hopper and starts dumping, we start losing some of those flock filters that we were counting on, the blue guys. And this graph is really like the origin of the animation that I showed about what must be happening with the fact that we have finite capacity in a flock. And once it is full, it's no longer useful. And we would like those to be the ones that leave, but unfortunately, our system for getting rid of flocks is also getting rid of flocks that would have been useful.